Hello everyone, I hope you're having a wonderful day. Welcome back to Aerospace Lab 2. Today we are going to continue the discussion we have had so far for the vibration lab, and we talked about the theory, the vibration theory we are going to use in the lab. The next step is to talk about data acquisition systems and in general data acquisition and the importance of it for experimental analysis. Okay, so data acquisition systems usually uh, consist of different components that can be integrated to these. We have the physical system that is giving you the data, right? Then you have a transducer sensor that senses your physical variables. So let's call this number 0. Then you have number 1, transducer section that senses your physical variables. Then you have the signal conditioning part that essentially cleans the uh, transducer, the data that is read by the transducer. Then you convert that data to using a analog to digital converter. So up until this point, we have the analog information. After this, we will have a digital data that is readable by a computer. So the final step is to make it readable by the computer, which is through the binary variable. Okay, and the example here is an 8-bit binary code, which means that you have 8 bits, right? These are the number of bits you have. Okay, so this is how data acquisition process plays out in general. The main reason we have this data acquisition process in place is the fact that you cannot analyze the analog data from the physical system by a computer without any connecting process. We need to have a connecting process. In the old days, what they did was they had on the physical system, I mean, not in the old days, a lot of people still do this. They had like a flow meter, whatever, if you're dealing with a fluid analysis, temperature controller, strain gauge, and they read the numbers directly off the gauges. Right? In the age of computers, in the modern age, we don't want to do that anymore. So instead of acquiring data by hand, you will acquire them by the computer. And this is the process you have to go through to be able to read the data by a computer. Okay. So, but what do these sensors and transducers do? And what can they measure or what can they sense? Sensors and transducers are devices that are there to sense physical phenomena and translate it to electric signals. Right? Examples is that it can sense temperature, pressure, light, force, displacement, level, electric signals, or digital signals. Actually, all of these are analog signals, and this one specifically is a digital signal, meaning that it has binary choices, either off or on, but the rest of them are continuous. We also, you will see the displacement signal in your labs. We are not gonna see temperature or pressure or light or force signals in the upcoming 2 labs. Later on, hopefully we'll see them. Okay. And then the sensor, when you read this data using transducer, this electrical signal must be conditioned so they can be read by an analog input board. We can do this type of conditionings on a signal. We can amplify them which means that you want to increase the signal power for more detailed or easier read. You can isolate them, essentially remove the noise or input-output interference. You can filter them, remove the noise or unwanted frequencies. You can linearize them, meaning that you want to make an output proportional to the input. So this linearization part is actually can be explained better with a graph here. For example, you may read and get input of voltage or the other way around, right? And you want to get output of the force, right? The force may be something like this, but you want to find a correlation, linear correlation that will give you an idea of what the distribution of this relationship looks like. Okay. And we have a lot of instruments we can use for signal conditioning. For example, this is a signal amplifier system. This is a very old system. I just have it here for example. But you can see all of the different properties it can do and all of the different things it can do with your signal, essentially, which is just amplifying it. Okay. Well, what does an analog to digital converter do, or AD converter? Right? It is obvious from its name. It essentially converts an analog input, which is voltage or current, usually, to a digital number, which is proportional to the magnitude of that voltage or current. Right. So in doing this analog to digital conversion, there are a lot of things that you need to consider, a lot of factors. You need to take into account the input signal that you're receiving. You need to take into account the sampling rate you want to have, the resolution you want to have, the throughput range. And again, we will talk about this a little bit just to make you guys familiar with the stuff. But these are not going to be, you're not going to be asked about them in a quiz or an exam. So an input signal can be analog, which means that your signal is continuous. Examples are strain gauge, which is a device we are going to use in the vibration lab. And most transducers produce analog signals, but your signal can be digital as well, which means that it may not need any conversion. Your signal is either on or off. It definitely needs a conversion, but we don't want to go into the discussion about that. An example of it is like a light switch that can only be on or off, a binary solution. So what does an AD converter do to your input signal? Let's say you're dealing with temperature. You define ranges for temperature. These is based on your sampling rate. Essentially, see 0 to 5 degrees in your analog input as 0, right? And the sampling rate here is 4 bits, right? Keep in mind that whatever that goes to computer must be translated into binary, right? Then your 5 to 2 will be 0001, which stands for 2, right? If you want to bring it to the tens, but in binaries will be 001. When we have all other ranges that you can see here. Okay, so essentially, if your analog signal looks like this, your digital signal will look like this. Okay. Depending on your sampling, and you usually want to have a better sampling rate. And what is the sampling rate again? It describes how often convergence takes place. The higher the sampling rate, the better, of course. And examples of your sampling is, if you, let's say you have an analog input that looks like this, as I said, if you have 4 samples per each cycle, these are the points when you are reading the sample. So your wave will look like this. If you have 8 samples per cycle, these are the points that you are sampling. So your wave looks more like the original wave, and if you increase the sampling rate, you essentially are going to increase the accuracy. But there are some reasons that you may want to have lower sampling rates. Among those, the first one is always how much sampling rate you can do based on the devices you have. Maybe your computer is a very slow computer, or the hard drive is limited, so you have to limit the amount of sampling rate. Also, the processing power required to handle a higher sampling rate goes higher. It's definitely going to be higher, so you always have to take these type of considerations into account as well. And sometimes the extra precision obtained by a high sampling rate is very unnecessary. Okay, so you don't need a high sampling rate. So these are the reasons that may force you to choose a lower sampling rate compared to a higher one. But in general, you want to have a higher sampling rate. The resolution you're going to see, of course, is directly related to the sampling rate. Using this equation, of course. But in general, as a rule of thumb, for each sampling rate for a 2-bit conversion, you are going to have only 4 values, meaning that a 2-bit conversion is this: 0, 0, 0, 1, 1, 0, and 1, 1. That's the only thing you're going to get. So only 4 sampling each cycle. You can have 4 just samples each cycle, right? For 3-bit conversion, 8 values are possible. For 5-bit conversion, 32-bit values are possible, but in general, it's a rule of thumb. For each n-bit conversions, 2 to the power n values are going to be possible. We are dealing with binary. Okay. Throughput is the effective write rate of each individual channel, which is inversely proportional to the number of channels sampled. For example, if you have a 100 kilohertz maximum throughput and 16 channels, it means that each channel has a 6.25 kilohertz throughput per channel. Okay, so higher throughput doesn't really mean that your channels each individual channel are giving you a very high throughput. It really depends on the number of channels that you have as well. The range is, of course, the maximum and minimum voltage level that an AD converter can quantify. Ranges are usually selectable, either by hardware or software, to accurately measure the signal. And your gain is essentially, we usually are concerned with the gain error. Okay. The gain error is the amount of deviation from the ideal or true slope of the AD conversion transfer function. Gain error can be corrected in the digital system by multiplying a signal conversion by a scaling factor. So you usually know the gain error, or you can calculate the gain error. That's the idea. But the part that we are really interested about, or we are interested in, is the data acquisition software, because we as mechanical engineers or as aerospace engineers, you are not really interested in how to convert the data. That's the job of an electrical engineer or a computer scientist or engineer. So we just want to do the experiment, and we want to be able to read the data. Okay, so we usually go out and buy data acquisition software, or we can write a code of a data acquisition software. So data acquisition software is the most critical factor in updating reliable high performance results for us, right? It essentially transforms your hardware to a complete display analysis and display system. We're going to see what this means later on. We have two different alternatives, as mentioned, for data acquisition software. We can program a software essentially, or buy a software package. And the second option is what we want to do. Buy a program software involves the use of programming languages such as C++, Visual C, Basic. There are a lot of different programmer softwares. The advantages of these are flexibility, so you can always change the code to your need. But the problem is, of course, the complexity and the steep learning curve of that programming language. But the data acquisition softwares usually do not require any programming, and they are usually very general, and they enable us to design the custom instrument best suited to our application. The examples of these are TestPoint, SnapMaster, LabVIEW, DAD, we usually call it DOTISP, and DACY-Lab, etc. LabVIEW is the most common and the most widely used in the United States. Right? It has a very cheap student version as well. So if you ever interested in doing having a data acquisition system in your home, you can buy the LabVIEW for $20, something like that, a 6-month license or something like that. And yeah, so we are interested in LabVIEW, as I said, and a data acquisition software. But what are the factors you need to consider when designing a data acquisition software, or when designing a module for data acquisition software? You need to consider whether you want a fixed or mobile application, whether your input is digital or analog, what is the frequency of input signal, what is the resolution, range, and gain you want to have, is it a continuous operation or does it stop somewhere? Is it compatible? Do you have compatibility issue between your hardware or software, or are the drivers essentially available? And the overall price, of course, is a very important factor in your design. But to go to LabVIEW, we already talked about what is data acquisition and why we want to use it. But from now on, we're going to see an overview of LabVIEW. We want to develop an idea of what LabVIEW really is. You want to learn what graphical programming language and data flow mean in LabVIEW and get a feel for the LabVIEW environment. And we want to learn virtual instrument programming through examples. These examples are essentially what we are going to do in the lab. That is going to be Thursday next week. I can't remember what it is. So today is September 16. So Thursday next week is going to be September 24th, I guess. Somewhere Thursday in the week of 24th. Okay. So this is what we are going to do in the lab. We are going to write down some examples. We are going to test those examples, and then we are going to write a program for our specific need, which is read a strain gauge data from a vibrating beam. Okay. A LabVIEW is an abbreviation itself, as is most of the software's names in engineering. It stands for the lab part comes from laboratory, and it essentially stands for Laboratory Virtual Instrument Engineering Workbench. Okay, it is a graphical programming language that allows for instrument control, data acquisition, and pre and post processing of the acquired data. It relies on graphical symbols rather than textual language to describe program actions, which makes everything easier for us. And the principle of data flow is present, which means that functions execute only after receiving the necessary data. Yeah. And LabVIEW programs are called virtual instruments or VIs because their appearance and operation imitate an actual instrument. They are analogous to the main programs, functions, and subroutines from popular languages. We're going to see this a little later. So this is an example of a VI. So if you write the code for, let's say, for latent heat measurement, this is what you are going to see in your VI. That, as you can see, it directly imitates your experimental setup. Okay. In LabVIEW, you can create or use virtual instruments or VIs for data acquisition. A VI will allow your computer screen to act as an actual lab instrument with characteristics tailored to your particular needs. So essentially, if this is what you're going to see, or a variation of this in the newer versions that we have. When you open LabVIEW, you want to always create a new VI, or if you have already written a VI and you can just open the VI. We can also build examples or use the standard templates that LabVIEW already have using this option here that will fit our data acquisition needs, essentially. The LabVIEW VI has different components. The first component is something called the front panel, which is an interactive user interface of the VI. It is named because it can simulate the front panel of a physical instrument. And the block or wiring diagram, which is this is your playground essentially. It is the VI source code constructed in LabVIEW's graphical programming language. G, it is the actual executable program. So whatever code you write for the LabVIEW is called the G code, right? It doesn't really look like a code. It's more. If you have ever worked with MATLAB Simulink, the codes you do for LabVIEW are essentially very close to MATLAB Simulink as far as how they are represented. So you're designing a system of blocks and diagrams in a G code. Okay. We also have the subroutines in a block diagram of a VI that we're going to see later on. The other parts that you're going to see in your VI is going to be your icons or connectors. If you want to put it simply, the front panel is the window through which the user interacts with the program. When you run a VI, you must have the front panel open so that you can input data to the executing program. The front panel is where you see your program's output as well. And the front panel is primarily a combination of controls and indicators. Again, an example of the front panel. But we need to talk about each part of the front panel. Now, there is a difference between control and an indicator. A control is an input from the user, source terminal. But an indicator is an output to the user, destination. For example, you give your sampling rate can be a control, but the frequency you're going to see is an indicator or the output that you can see. But we can, of course, transform these two to each other. We can change them in a VI code by just simply right-clicking on them. You can right-click on an indicator to change it to a control or change the format to anything you want, like a precision or whatever, right? You can right-click on a control to change it to an indicator or change the mechanical action. We're going to see the examples of this in the lab. The block diagram window essentially holds the graphical source code of the LabVIEW virtual instrument. and it is the actual executable code. So this is an example of G code. You essentially construct this block diagram by wiring together objects that perform specific functions. The various components of block diagrams are terminals, nodes, and wires. So let's talk about the terminals first. Terminals are essentially when you place a control or indicator on a front panel. LabVIEW automatically creates a corresponding control terminal on the block diagram. Okay. Control terminals have thick borders, but indicator terminals have thin borders. So this is a control terminal, this is an indicator terminal. You can always delete them. Delete the control terminal. If you delete them here in your workbench, if you will, it will be deleted in your front panel as well. What are nodes? Nodes is just a fancy word for a program execution element. Nodes are analogous to statements, operators, functions, subroutines in a standard programming language. We can, the very simplest example of a node is the add and subtract function, which represents a type of a node, as I said. A node can be a structure as well. Structures can execute code repeatedly or conditionally, similar to loops and case statements in traditional programming languages. LabVIEW has also special nodes called formula nodes, which are useful for evaluating mathematical formulas or expressions. Yeah. A LabVIEW VI is held together by these wires, as you can see here. So essentially, your digital controller sends the data to this node and then sends it to a digital indicator by these wires. We have different types of wire, which means that which refer to the different type of data they are transferring. So each wire has a different style or color depending on the data type that follows through the wire. For example, if you are dealing a floating point number, and if it's just a scalar, you will see an orange thin line. If it's a 1D array, you will see an orange thick line, and if it's a two-dimensional array, you will see a double line. The same is true for an integer, boolean, and a string that is going to be transferred through a wire. So you have to be familiar a little bit with the data structures, but I think at this point you should be pretty familiar. But if not, you can always come to us, me or the TA, and ask your questions. Okay. You always have to keep in mind that if you connect more than one source or no source of wire, it will be shown like this, which means that LabVIEW disagrees with the type of operation you are adding. It will look like a broken wire. It is a dashed line, so you have to fix that. So this is essentially a form of debugging that LabVIEW directs you towards, like debugging the problem that you have in the block diagram. You may think to yourself that this is a very simple matter, you will never get into these problems, but most of the LabVIEW block diagrams are very huge for the real experiments. So these type of problems are very likely will happen. Okay. What are the different components of the block diagrams? As we said, just a recap, nodes are that program that are essentially program execution elements, are terminals, which are ports through which data passes between the block diagram and the front panel, and between nodes of the block diagram, and wires, which are the data path between terminals. Well, data flow programming simply stated is means that a node executes only when the data arrives at all its input terminals. The node supplies the data to all of its output terminals when it finishes executing, and the data passes immediately from the source to the destination terminal. But the icons and the connectors, so essentially, if you let's look at this uh, node, if you will. But the data flow programming here means that you have to receive all of your inputs before processing anything, right? When you have received all of your inputs, it will give you an output of the new temperature, for example. Otherwise, you will not receive an output, right? So you always have to be mindful of the icons and connectors. The icon is a graphical representation of the BI block in the diagram, and the connector defines the input and the output. Right? The connectors, the icon. Simple representation of the front panel on wiring diagram. It is often helpful to view both of these simultaneously. Just snap the windows to different side of your display, and yeah, what will happen? Modifying a VI is done through essentially modifying your not the front panel, your block diagram panel, essentially this one, and then it will automatically be modified in your front panel. These are the options you have. For example, if you choose this, essentially it will operate in a control if you click on something. If you choose this, it will select a feature to edit or move it. If you do this, it will add or edit the text. It will probe the data. If you choose this, it will, I'm talking about the clicking operation, right? So if you click and if you choose any of these operators, it will do these operations, right? And if you want to wire, you have to choose this operation and so on and so forth. The other window that you see is the window of controls. You can insert the Boolean control or on and off switch by choosing this. You can insert a digital indicator control by choosing this. And it may be a little confusing to you guys at this point, but that's all right. We're going to see all of these in the lab. So I'm not going to go into the discussions of this because you can always go over them yourself, and these are pretty self-representatory, self-explanatory, if you will. And yeah, so I'm just gonna stop on each of them for a couple of seconds so you can take a look at what each function does and move on to the next one. Yeah. Keep in mind that each palette has a different sub-palette. So if you click on this, for example, a sub-palette will open, and it will give you many more options. And so this is the discussion we are going to have for this lecture. Next week in the lab, we are going to go through these two examples, so make sure to go over them. And then we are going to design what you need for the original lab. So see you guys in the lab, and have a wonderful day.